Hello, my friends. Today we are going on, and I want today to discuss about atomic spectrum. So, spectrum is the arrangement of characteristic frequencies of electromagnetic radiation absorbed or emitted by an atom. So, basing on this definition, spectrum can be radiations absorbed by an atom or radiations emitted by an atom. So, arrangement of the frequencies of the electromagnetic radiations absorbed or emitted by an atom, or in other words, spectra is the arrangement of radiation in order for increasing frequency or decreasing wavelength. So, these radiations, they may be absorbed by an atom or emitted. Now, when we are going on the types of spectrum, if an atom is emitting radiation from it, we call it as emission spectrum, and if an atom is absorbing radiation into it, we call it as absorption spectrum. Now, these two types of spectrum means emission spectrum and absorption spectrum. They are divided furthermore into three categories, which are line spectrum, band spectrum, and continuous spectrum. Emission spectrum, by definition, is the arrangement of electromagnetic radiation emitted by an atom due to an atom's electron transition from high energy level to a lower energy level. As we discussed in the previous lecture, that electron transition from high energy level to lower energy level lead to the emission of energy it absorbed when it was excited. So the light or the energy which is emitted can arrange itself into different wavelengths or into different frequencies, and that when we view it, we call it as the emission spectrum. On the other hand, absorption spectrum is the arrangement of frequencies of electromagnetic radiation absorbed by an atom. Absorption spectrum does not contain all radiation of all wavelengths. So absorption spectrum just contains few wavelengths as compared to emission spectrum. So in appearance, emission spectrum appear as a black, then it has lines of different color, while the absorption spectrum appears white, while it has dark lines within it. So that is the major difference between absorption and emission spectrum. Now, line spectrum, all of these two categories, they are divided furthermore into three categories: line spectrum, band spectrum, and continuous spectrum. Now, line spectrum is the emission spectrum with only certain frequencies. It is produced by excited electron and ions as they fall back to a lower energy level. So in line spectrum, the spectrum forms distinct lines. There are distinct lines in the spectrum. While in band spectrum, lines, they are arranged in groups, closer in one side and far apart in another side. So band spectrum is the one which consists of well-defined group of lines. That's why they are called band spectrum. The lines in each band are closer to one side than other. Here they doesn't illustrate, but in reality they could not require to appear like this. So band spectrum lines should be close on one side and far apart on the other side, as you can see in most of the books they have explained this. So band spectrum consists of well-defined band of lines, group of lines. While continuous spectrum, the emission spectrum with all the wavelength or frequency of visible light. So continuous spectrum have all the wavelengths. Remember, in line spectrum, we have distinct line, means it has few frequencies. In band spectrum, we have group of lines. In continuous spectrum, this is the spectrum with all wavelengths of frequency of visible light. Now, let's go on to hydrogen spectrum. Hydrogen spectrum is the line spectrum. That's the first thing you must know. Hydrogen spectrum is the line spectrum. So hydrogen spectrum, by definition, is the series of radiation which are formed when a hydrogen atom is excited by heating. Spectroscopic analysis technique analyzes that hydrogen spectrum has 3 regions which are named on honor of their discovery, such that Lyman Series, Bure Series, and the Planck Series. So it's not true that hydrogen spectrum have only 3 regions. It have more than this. But here they have analyzed these 3 regions. Now, you must know this in a hydrogen spectrum because sometimes they ask you to define what is a Lyman series, Bure series, or Planck series. And sometimes, if not to define, they may ask you any question about hydrogen spectrum and ask you about this. So, because I want to make my students competent, I'll produce another video about hydrogen spectrum using other notes or another book so as to make you more competent. But what thing you have to know here, hydrogen spectrum, hydrogen atom has 1 electron. So when it is given energy, that 1 electron can be excited to a certain energy level. When it is coming back to its ground state, which is N1, the electron can emit energy. So that energy which is emitted appears a line spectrum. Now, Lyman series is the section of hydrogen spectrum whose radiation results from electron transition from high energy level to energy level 1 or to the first energy level. So in Lyman series, as you can see in the diagram here, we have N1 below here, we have N2, N3, N4, N5, and N6. So in Lyman series, these are ultraviolet. Electron must fall from any of the high energy level to the first energy level. This is Lyman series. Then in Bure, electron must fall from high energy level to the second energy level. The section of hydrogen spectrum whose radiation results from electron transition from higher energy level to energy level N2. Now these are Bure series. Bure series is the only visible series or the only visible part of hydrogen spectrum. So if they ask you, the visible part of hydrogen spectrum is Bure series, only Bure series. We don't have any part of hydrogen spectrum which is visible rather than Bure series. So here they appear in different color because of different wavelengths. Lyman is ultraviolet and the Planck is infrared. Other series they are infrared, but Bure is the only visible part of hydrogen spectrum, or the only part of hydrogen spectrum which can be seen by naked eyes. Now, Planck series is the section of hydrogen spectrum whose radiations result from electron transition from high energy level to energy level N3. So hydrogen spectrum is represented as horizontal lines like this. Here there are many things to understand. Many. As you can see from N1 to N2, here there is a great space between N1 and N2. Between N2 and N3, the space is somewhat decreased. And if 3 and N4, these lines, spaces, as you are going, the lines, they become closer and closer. So the cause of the line to become closer and closer is what will cause the line to converge, and where the lines will converge is what we call is convergent limit. Electron excited from N1 line to more than that limit will be out of the electrostatic attraction by the nucleus, and that electron and that atom will be said to be ionized. So the arrangement of color in a visible region are shown in this row here. So these are the arrangement of color in visible region. Means these are the arrangement of color in Bure series. In Bure series. Now, the relationship between wavelength and energy level. The equation which shows the relationship between wavelength and energy level is given below. So the equation is like this. This is called the Rayburg equation, but it is the equation which we are normally using in the calculations of wavelength and energy level in the hydrogen spectrum. Different things can be done here in this equation. You can calculate frequency, you can calculate velocity, and things like that. Many maneuvers and manipulations can be done from this equation. So I beg you to follow up in another video which I will produce about demonstrating the use of this equation in calculations. So this lambda means wavelength, N1 is the original energy of an atom, and 2 the level of an electron in excited state. Remember, N1 here is the lower energy level, despite an electron is being excited or it falls from higher energy level. So for example, when an electron comes from energy level 4 to energy level 2, N1 will be equal to 2 because 2 is nearer the nucleus compared to 4, and 2 will be equal to 4. Don't assume that N1 is the original position of an electron, because if you assume that N1 is the original position of an electron, you can take here N1 is equal to 4, which is not correct. The value of N1 must be smaller than N2. So in short, N1 is the energy level which is closer to the nucleus, and to the energy level of an electron in excited state. So N2 must be a bigger number than N1. RH is Rayburg's constant and its value is like that one, while that one is wave number. So different maneuvers can be done from the equation to calculate frequency, wave number, and things like that. Here there are some worked examples. For example, you are given speed of light and released by constant. Then you are told calculate the frequency of third line in visible region of hydrogen spectrum. Now, according to this question, we are going back to the hydrogen spectrum. Third line of visible series. According to this question, calculate the frequency of third line in visible region of hydrogen spectrum. Remember, I told you that the only visible region of hydrogen spectrum is Bure series. So now, the first line is the electron falling from N3 to N2. The second line is the electron falling from N4 to N2. The third line is the electron falling from N4 to N2. I hope everybody remembers what I've done here. I'm repeating. The first line is the electron falling from N2 to N2, from N3 to N2. The second line, electron falling from N4 to N2, and the third line from N5 to N2. Now, according to how I told you that N1 must be a smaller value, so N1 here is 2, and N2 is 5. We are counting from the line which is shorter, and then we are going. So the first line here is from N3 to N2. Don't count as the first line is from N6 to. The series of counting, we are starting here the shorter line. So that's how we can know the values of N2 and N1. And here in your calculation, you can include the diagram which can draw that hydrogen spectrum and show the lines which could illustrate to your teacher that N1 is equal to 2 and N2 is equal to 5. Now, having already known N1 is equal to 2 and N2 is equal to 5, you just compute your values in the Rayburg equation and then you get your answers of frequency. And the example here, given part of hydrogen spectrum can be represented by the equation, that one. What do the symbol lambda, RH, and N2 represent? Lambda is the wavelength of hydrogen spectrum. RH is the constant, while N2 represents the energy level of excited electron in hydrogen spectrum. What is the unit of lambda, that one and that one? As you know, the unit of lambda is per meter. The unit of Leslie constant, as it is seen here, it is per meter. It is per meter also, and the unit of N is the energy level, so it does not have unit. Calculate the wavelengths of the first line in Obama series of hydrogen spectrum. Now, as you know, Obama series is the electron coming from high energy level to N2. And here the first line of Obama series is from N3 to N2. I hope I have explained this in the first question and you all know this. So, I hope you have a good understanding about this. If you are told the first line maybe in Obama series, in Lyman series, or in Planck series. For example, if you are told the first line in Lyman series means is from N2 to N1. First line in Planck series from N4 to N3, and etc. etc. So here in example 3, it is solved here. As you can see, N1 is equal to 2 and N2 is equal to 3. They have just substituted here and they get the value of wavelength, then the value of frequency. Another example here, example 3, calculate the wavelengths of a line in a Obama series that is associated with energy transition. Energy 2 is equal to that one and energy 4 is equal to that one. So here there are two energies, energy 2 and energy 4. Remember, the energy of an electron decreases as it is moving away from the nucleus. What I mean is that the ionization energy of an electron in the fourth shell maybe has the smaller attraction to the nucleus as compared to the electron in the second shell. That is because the attraction between the nucleus and the electron is the electrostatic attraction. But remember, in the Coulomb's law, that if you want to get force will be equal to constant, then Q1, Q2 divided by R square. Remember, R square here is the distance separating the two charges. Now, having already memorized you the Coulomb's law of electric current in physics, or if you don't know it, worry out. But what I want to explain here is that force is inversely proportional to the square of radius, or the square of the distance separating the two things which are attracting together in electrostatic force. So, if force is inversely proportional to the square of distance separating two objects being attracted together by electrostatic force, means that if the objects they are too far, the force will decrease. So here, labeled E2 negative 5.44 times 10 power negative, that is more attraction as compared to negative 1.36. So it's not easier to understand me if you have not done the current electricity or the electrostatic in physics. But if you do physics, it is easier to understand me. If you don't do physics, if you are studying CBG, if you are studying things like that, worry out. But here, one thing you have to understand, E2 is closer to the nucleus than E4. So now, as you have already known about the energy, we are going back into the what we call the Planck's equation. If you remember, in the Planck's equation, energy was equal to Planck's constant then frequency. Now here you are calculating change in energy. Change in energy. And change in energy, here, change in energy, it was equal to E4 minus E2. Because E4 is the energy of an electron at energy level 4. And E2 is the energy of an electron at energy level 4. At energy level of 2. But here I think this teacher has done a mistake, because this value of E4 was a negative value. was a negative 1.36 minus negative. So this value of 5 could become positive, but this could be negative as it was. So that's all. Question number 4. The energy of an electron in a hydrogen atom when it is ground state will be given by the equation. Energy 1 is equal to that one joule. The energy of the same electron if occupies a high energy level, and 2 energy 2 is equal to that one. Data given. Now they want you to calculate the energy of an electron as if there is no question here, but I don't know. They want you to calculate energy. Okay, they want you to calculate energy, and the question is short like that. If there is any problem, you can consult me, but I will just upload an independent video explaining about these questions. As you can see here, they have given you wavelength of first member in Lyman Series and Ionization Spectrum with that one. Calculate the wavelength of the second member of Lyman Series. This question, be careful now. This question is very tough. It's very tough. You are given wavelength of first member in Lyman Series. One thing you should do here is to calculate Lyman constant. In a question like this, we don't use the Lyman constant we know normally. So you are calculating it from your wavelength. Now you're using this equation, and as you have already known, the first member of Lyman Series means is from N3 to N2. You are calculating the value of wavelength. Then after calculating the value of wavelength, you are calculating the value of Lyman constant. After calculating the value of Lyman constant, now you are going on to calculate the value of wavelength using the value of Lyman constant. And as you know about Lyman series, the second member of Lyman series means is from N3 to N1 as it is demonstrated here, and then you finish. So all these calculations I will demonstrate them in the calculation videos, but also you can calculate about the energy of an electron in its shell. Electron in its shell, and it is represented as energy of an electron is equal to negative 13.6 E divided by n squared. Now E is the electronic charge, which is 1.6 times 10 power negative 19 coulomb, and N is the energy level of an electron. So here there are worked examples, and I think for this topic it's over. We can calculate these questions next time. And as you see, there is a concept of ionization energy. Concept of ionization energy. Ionization energy is the energy needed to remove an electron completely from its atom. Ionization energy can be obtained from the Planck's equation. Now, from the Planck's equation, which is energy is equal to Hf, we have derived this to that equation, which is energy is equal to negative 13.6 electronic charge divided by n squared. Now, in the ionization energy, n is infinity. N, which is shell, is infinity. But as you can see here, ionization energy can be calculated as Avogadro's number, then Planck's constant, frequency. So, for example, here calculate the amount of heat energy required to remove an electron from N5 to infinity. So the energy needed to take an electron from N5 to infinity is equal to the energy difference between the two energy levels. So two energy levels means the first energy level is N5, but the second energy level is infinity. And if you put infinity here in this equation, which is negative 13 times electronic charge, then divided by infinity, you will get an infinite answer. So simply, you can't get that. About Bohr atomic theory, we already discussed these, but we are just memorizing them. And here, the electron revolve around the nucleus in particular paths called orbits. Then each orbit have different amount of energy, hence they are called energy level. When an electron jump from one energy level to another, it emits or absorb energy. Angular momentum of an electron is quantized. So if it is quantized, it means it have a certain fixed value. Here we are calculating mvr is equal to h divided by 2 pi. So this is the equation, you must know it. M is the mass of an electron, v is the velocity, that is the linear velocity, and r is the radius. So that is not circular velocity, it's the linear velocity. Discussing some of the success of Bohr atomic theory, he managed to explain the Lyman equation. He managed to calculate the radius of hydrogen. He explained the hydrogen spectrum, determination of energy of an electron when it is in a stationary state. So these are success and the weakness they are here. Weakness or drawbacks: if we to explain effect of multi-electronic atom, if we to explain splitting of spectral line when subject to magnetic or electric field. He was challenged by Heisenberg that is impossible to determine both velocity and the position of moving electron at the same time. We shall see it later. Heisenberg uncertainty principle. Then he failed to explain quantization of energy. He failed to explain shape of a molecule, that is shape of orbit. He failed to explain relative brightness of spectral lines, that is why some of the spectral lines they are bright and some of them they are not bright as others they appear. So for today, let's end here. Next video, I'll be discussing about atomic number, nuclear rotation, and all about the mass spectrometer and all the calculations, principle of working, and all of these questions they are asked directly. Thank you, everybody. I am continuing to invite you in my Telegram group. Remember, I'm just using my time doing these videos. Sometimes people can think maybe as if I'm paid, but sometimes you should know that I'm doing this in my own risk. That is, I'm losing my time to help the students. However, maybe not all of the things will be perfect as how you want, but most of the things you can learn them free. It's not as if you could go to tuition, and you access notes free on Telegram. So welcome anybody, and there in Telegram you can access me more simply rather than in YouTube. I will put a link in the description, and I beg you to just continue following my videos so as you can get more and more.